There is no metamorphic process that does not involve heat. So whether you're talking about contact metamorphism, dynamothermal, hydrothermal, heat is always a factor. But in this case, the dynamo refers to pressures now. We're going to talking about a combination of increased pressure and temperatures. Well, then just picture now, just based upon what we've learned in this course up until now, what environment do you think of when I picture high pressures and high temperatures? Of all the places we've talked about, you got to start thinking zones of subduction. I mean, we're talking here the biggest head-on collision in the world. There's no place on Earth that has the compressive forces that are developed like in those zones of subduction. So the amount of dynamic business, the pressures are enormous down there. Of course, the temperatures are too. As that plate descends down in further and further into the mantle, things are heating up all the time. And as a result, you have this combination now of dynamo-thermal metamorphism. Now, picture now how big this place is. A typical zone of subduction. Well, think about the western margin of South America. We're talking about a zone of subduction. Certainly it's thousands of miles long. What would be the three dimension? I expect down there, if you're talking about where's the influence of this zone of subduction, it certainly would be hundreds of miles wide and probably hundreds of miles deep. So we're talking about a vast mass of rock down there that's being converted as a result of dynamo-thermal metamorphism. But note once again, we've added nothing, we've taken nothing away. All we're going to do down there within this massive zone, we're simply going to take minerals that are already there. We're going to take the minerals that are in the basaltic oceanic crust that's being subducted. We're going to take the minerals in the gabbro, which is the same as basalt, of course, but that's being subducted. We're going to probably take some of the peridotite in the upper portion of the mantle. That's all part of the subduction zone. We may even take a little bit of the granite, which is the edge of the continent. So you see, we have an assemblage now of different minerals that we can use to convert into other minerals. But the point is, all we're going to do is simply take what's there under the new conditions and turn them into a new assemblage. We've added nothing, we've taken nothing away. Now, again, going back to the size of this thing, how do we know what went on at all? Well, think about, again, two continents colliding. That would be the ultimate now in a head-on collision. Let's say two continents collided. Millions and millions and millions of years later, these two collision places come to the surface, and now we're exposed. For example, the collision of the continents that created Pangaea. That created the Appalachians. That all was going on somewhere down in that collision zone between the two continents that ended up making the Appalachians. Well, we can see them now. They're at the surface now. We could go, for example, into what we call the Piedmont, and that's where we see all these metamorphic rocks. If you go to the Piedmont, which would be that part of the Appalachians, just to the east of the Blue Ridge, unfortunately, a lot of it goes under the coastal plain where we can't see it anymore. But the rocks that are exposed in the Piedmont, those are the metamorphic rocks that were down in that zone of subduction when those two pieces of Earth collided to each other. So we can now see them. It's obviously hundreds of millions of years later, but that would be an example of our dynamo-thermal metamorphism. Now, since it covers a big area on the surface, some people would refer to that again as regional metamorphism. It's not a different kind of metamorphism. It's simply that it's exposed over an entire region like that. And, for example, again, they would go in, and depending upon where you were relative to the actual collision site, there would be zones of different metamorphic minerals that you would be able to identify, indicating where you were relative to the collision site. So there's all kind of things these metamorphic people do to try to reconstruct a zone of subduction that existed 250 million years ago. And you see, that's what geology is all about, trying to figure out what it was like 250 million years ago. So that's the dynamothermal. Now, the hydrothermal is something different. Again, heat's in there. We're talking thermal here. But the hydro part, that's the chemically active fluid. That's where the chemically active fluid comes into play. Now, the chemically active fluid, it sounds pretty hairy, but what it is really hot water. But remember now, water is the universal solvent. It will dissolve more things than any other solvent known to chemists. Molten rock dissolves more than that, but that's another story. So anyway, here we have now hot water. Question. Where does the water come from? Well, let's go back for one thing to that zone of subduction. Now, down in the zone of subduction, we just talked about the dynamothermal, but there's also hydrothermal going on because there is water involved in the zone of subduction. Question, where does it come from? Well, there are a couple of sources. For one thing, here we have this oceanic lithosphere plate diving down into the zone of subduction, and right above it, of course, we've got the ocean. Now, what do you think the possibilities are of some of that oceanic water being drugged down into the mantle along with that descending plate? Well, I think it's probably pretty good. And so there's one source of water. I don't know how much that represents in that volume, but I suspect it's probably appreciable. And remember now, in terms of chemistry, that's not pure water. That's water with a lot of stuff dissolved in it. That's why it's salty, you see. There's stuff dissolved in it. So here we have a chemical solution, if you will, being pumped down into this zone of subduction that can do some other things down there. Now, there are a couple of other sources of water that are also being taken down into the zone of subduction from the ocean. You'll have to take my word for this, but all over the world there's dust settling out on the ocean surface. These are just dust particles that are picked up as the wind blows across the land and is hauled over the seas, and they fall out on the ocean surface. They fall to the ocean bottom. So if you were to go to the ocean bottom, chances are, rather than actually seeing the absolute surface of that oceanic basaltic crust, it probably would be covered with at least a little thin layer, relatively thin layer, of these sediments that fall through the ocean, just dust from above. Well, if you look at some of those sediments now, think about it, they're going to be drugged down into the zone of subduction along with that descending plate too. Now, if you look at some of the minerals, if you see a mineral and it's written, let's say, AB dot water, thinking a little of your chemistry now, AB dot water, that's a chemist's way of saying that there is water tied up in this mineral. Now, the dot implies that it's not very tightly held. Case in point, the mineral gypsum. We talked about gypsum. The formula for gypsum is calcium sulfate dot 2 waters. You could take gypsum home, put it in your oven in your kitchen, turn your oven up to maybe 450 degrees, and that's Fahrenheit now, and what would happen is that bond, that dot bond, would be broken, the water would be taken off, dehydrated, and what you'd have left behind is just calcium sulfate, which is anhydride. So you see, that the way a chemist has of saying the water's there, but it's not very tightly held. Well, there are minerals being drugged down into that zone of subduction that have formulas like that, those dot waters. But here's another one. Another way the chemist has of saying there's water in this structure of this material. Let's say you have a formula AB with a hydroxyl in it. Anytime you see a hydroxyl, that OH, that's another way of a chemist saying there's water in this structure. Because if you take things that have hydroxyls like that and you heat them up, you're going to have to do it to higher temperatures though, because that's more strongly held, you'll drive off water. Case in point. Take calcium hydroxide, CaOH twice. If you take calcium hydroxide, now this would take more than your home oven would do, but let's say you put it in a furnace and maybe heated it up to maybe 500 or 600 degrees centigrade. What would happen? It would dehydrate, and what you'd end up with would be calcium oxide and water, 2 waters. In other words, the water would eventually come out there too. It took more energy to do it, but still it came out. So between those three, between water being drugged down, just seawater being drugged down along with the plate, and these two kinds of minerals that would provide water down in that hot zone, you do have water within that zone of subduction. And as a result, that water can then attack the rocks as they're being transformed. It can take things out of some of the rocks, put other things back. So now what's going to be the result? What the result is going to be that the metamorphic rock that's going to form is going to be not only mineralogically different from what you started with, but compositionally different. The elemental composition is going to be different. So now it gets a little bit more hairy, you see, a little bit more complicated. Now there's one other hydrothermal situation I'd like to describe because this one has some economic value, I think. Picture, if you will, a mass of molten rock being injected into the part of the crust. I don't really care where it is. Let's say, it's injected into this layer of sedimentary rocks that covers everything. Now it's going to sit there and cool off. Now, all molten rocks, all magmas contain water. Now, you have to take my word for it at the moment, but in another lecture, I think the next lecture, we're going to talk about volcanism. Whenever you see a volcano erupting, the big billowing cloud, of course, a lot of it's ash, I understand that, but a lot of that is just simply condensed water vapor or steam. The main gas